very full. I would normally wait like 2 minutes. I'm not sure we can actually fit any more people in here. Thank you all for coming. It's my pleasure to welcome you all to the Chapman Lecture in Nanotechnology. This is a special lecture. It moves between the electrical engineering department and the physics department. And it's made possible by a generous contribution from Richard Chapman and his wife Barbara Chapman, who are both proud Rice alumni. Yeah, that's the plural. Okay. I do want to mention a couple things about the Chapmans. Richard Chapman is an owl 3 times over, bachelor's, master's, PhD, all in physics, and according to my notes, was a star football player back when Rice was ranked number 6 in the nation. Yes, and beat Alabama in the Cotton Bowl. So I just want to think back about the glory days when we beat Alabama. And according to Wikipedia, I did not personally confirm this. Are you MVP of the Cotton? Can I get a confirmation on this? Okay, 1 of 3 MVPs. The number 1 of the 3 MVPs. So thank you. And thank you for supporting this lecture, seriously. And also thank you for turning down your first-round draft pick to the Detroit Lions. Instead, he decided to go. No, that's not a joke, serious. And then he instead had a remarkable career in engineering, working for GE on nuclear power, and then for Texas Instruments, where he kind of developed his love for nanotechnology that led to this lectureship. So we're very honored to have them here in the audience today. And thanks to this support, we've been able to invite a number of really fantastic speakers. This year we have Zhenan from Stanford, who made the trip out. A number of accolades for Zhenan. She's the KK Lee Professor and Department Chair of Chemical Engineering, courtesy appointments in Chemistry, Material Science, and Engineering, all at Stanford. Dr. Bao's known for a number of things, probably early on for developing technologies with organic field effect transistors and organic semiconductors. And I think one of the remarkable things is her insight during the development of organic electronics led her to think about application spaces that were at the time, I think, very futuristic. This idea of kind of combining transistors with biology, and kind of before bioelectronics had a name, she was kind of one of the leaders, the founders of the field. And what she'll talk about today is how this idea of kind of combining nanotechnology, field effect transistors, organic electronics with her training in chemistry is able to develop technologies that I think represent what we're going to see in the future. And I think what's, in the context of this lectureship in particular, it's really interdisciplinary work that Dr. Bao is working on. There's people from chemistry and physics and electrical engineering. I think we're going to see what can be done when we really cross traditional boundaries. So a number of her accolades include more than 500 referee publications, 60 U.S. patents. She was selected as Nature's 10 People Who Mattered in 2015. She's been awarded the ACS Award in Applied Polymer Science in 2017, the L'Oreal UNESCO for Women in Science Award. In the Physical Sciences in 2017, she's been elected to the National Academy of Engineers, National Academy of Inventors. So please join me in warm welcome for Zhenan Bao.
Thanks, Jacobs, and the department and the school for the invitation to speak here. And thanks, Dr. Chapman and the family for the sponsorship for this lectureship. It's my pleasure to be here and tell you about some work we're really excited about, which we have been pursuing almost over the past decade. The outline is here. I'm going to tell you about what we have in mind in terms of what we call the future of electronics is the electronic skin concept. And then that led us to develop or inspire us to develop future electronic materials. Then I will show some of the possibilities of using these new materials to enable soft electronic interface with human. Okay, so first let me ask a question to the audience. Who of you sitting here does not have a cell phone? Guess I don't see anybody. So we cannot, indeed, we're living in a time that we cannot imagine living without a cell phone. But the vision we want to propose is we can imagine a future without cell phone. That is, all the functions of cell phones are going to dissolve into what we wear, what we attach to our skin, and what we implant inside our body. So this is a very rough roadmap. This is kind of just a scientist or engineer's roadmap, so there's no exact year. But it's with time and then complexity of the electronics or network. And we are in the regime of, we say, transition from smartphones to wearables, entering into a new regime where we start to have more and more interaction between human and electronics. And this is very much the trend that we see that is taking place for the future of electronics. And we see that's how we are going to be in the future, connect with our friends, our surrounding, our cars, and our environment. And this is already happening with just as simple as a cell phone. So we started this area by thinking about how we enable a future of new electronics future by actually starting to try to mimic the sense of touch of human skin. We first tried to learn how to mimic, using artificial electronic devices, the individual function of the mechanoreceptors in the human skin that allows us to be able to sense external information. And also, remarkably, oops, I pressed the wrong button, sorry. And also remarkably, that the information of sensed from the, let me try this. Okay, see if this works. Oh, it doesn't work anymore. Let me just try one more time. This is supposed to be the high, oh, okay, I see. No, start. But, oh, okay, now it is. Okay, takes a little bit of learning, I think, for this project part. Okay, all right. And remarkably, with the sensing, it actually, our mechanoreceptor puts out digital signal in the form of frequency. And then that's being transmitted through our nerve system to get processed in our brain. So we started out trying to learn how we build such devices so that we can mimic the sense of touch, and then learn how to make it more complex. So for example, each green dot is an individual artificial mechanoreceptor that we build with a sensor plus a pressure sensor plus a simple ring oscillator to generate the electrical pulses. And then these mechanoreceptors can combine information into the synaptic junction, where we use a synaptic transistor to gather all the information to mimic this type of biological system in terms of sensing large amount of information. So that's how we started. But then after starting to work on these sense of touch, we start to look at what are the basic functions of skin. And basically, as an engineer, I see it in a very simplistic way. The skin has sensing functionality, signal processing to convert analog information into digital information, and biointerface. And these are essentially the functions we want to have for wearable electronics or future implantable electronics. And furthermore, skin is a fascinating material that actually is not only flexible, but also stretchable, biodegradable, and self-healable all at the same time. Even though flexible electronics are starting to appear on the market, but the additional properties are properties that are not yet built into our electronics. But if we can do that, then we can potentially turn today's rigid electronics and brittle electronics into these wearable electronics or foldable displays where the strain tolerance or good mechanical property is required for these electronics. And then towards more future to integrate electronics with human, then we want these electronics to be able to accommodate the dynamic movement of human body or the internal organ. And in both cases, for example, on beating heart or on brain, all these organs have expansion and contraction. So the electronics, future electronics also need to be able to accommodate the strain that's asserted onto these electronic devices. So that gives us the motivation to think about new generation of electronics. Of course, currently we're not the only group working in this direction. There are many groups working on various different aspects, ranging from developing new materials, new strategies for devices, as well as new applications. But the question that we're really interested in from more the fundamental side is to think about how we can design, because we think the key is really the materials. If we don't fundamentally change the materials, then we're not going to be able to realize the new functionalities that we envision. So the key question we ask is, first, how we come up with these skin-like electronic materials without compromising electronic property. And if we can do that, then we can start to build on that and make more complexity into the devices. So what we envision is here is a photo of our first generation artificial mechanoreceptor. It has the sensor and the simple ring oscillator that's printed onto flexible substrate. So this case is a flexible version, but as we develop new electronic materials, then we can start to make this stretchable, self-healable, or even biodegradable, or combination of them. And we can start also to learn how to make this mechanoreceptor to be more complex and start to really build a true e-skin that mimics everything our human skin can do. So that's really the very long-term vision that we have. So it comes down to how we design these materials. So the big challenge we face is even with plastic materials, polymers, they still are not mechanically robust. They form cracks very easily. We know silicon is brittle, but plastics can also form cracks easily. So the key design concept, which I won't go into too much detail, is basically these are molecular networks. These are polymers that we use to build semiconductors and conductors. And conventional rubber material have these covalent bonding to make a network of these polymer. So when you stretch the polymer, the flexible region or amorphous region will get extended, and once the force reaches certain limit, then these covalent bonds will start to break. And once the covalent bonds are broken, then the cracks are formed, and this is an irreversible process. But we're interested in a new class of material where these kinds of network is formed using chemical bonds that are essentially reversible, or they are at equilibrium under room temperature. And these chemical bonds they can still break when the material is subject to strain, but then they provide an energy dissipation mechanism to allow energy dissipation so that the overall total fracture energy of the material can be increased. But the nice thing is these bonds are reversible so that then the material can recover its original mechanical property or even electrical property because of the self-repair of these chemical bonds. So examples are chemical bonds that people have studied for a long time as for so-called supramolecular chemistry. There are various different type of bonds, and then the hydrogen bond is a type that we have used quite extensively. And just to give you an idea, the type of tuning one can achieve with different various type of bonds. For example, urea, this type of simple hydrogen bonding have association constant of 1, while if we use a design where there are 4 hydrogen bonding formed simultaneously, this is called the quadruple hydrogen bonding, then this will give association constant of 10 to the 5th. And then the last one essentially can give mechanical property, allow us to tune the mechanical property, and then the weaker ones allow us to incorporate energy dissipation mechanism into the material. So this is combining these different chemical bonds allows us to achieve the desirable mechanical property and also realize the potentially electronic property. So this is one version, an early version of the material that we have developed. And this is a version that seems the testing worked, but then somehow it doesn't. All right, so this is the one that's with weak bonding, so very viscoelastic. Then if we incorporate stronger bonding, this is with some covalent bonds together with the dynamic bonds. So this shows the material that's being cut. And then when the two pieces are put together, then the hydrogen bonding will start to recover, and that will recover the mechanical property of the material. So within a minute, we start to see the material is mostly recovered its mechanical property. But if you look closely, if you see the there's defects, then it will start to show cracks. So the best design that we found is with actually a combination of, I mentioned there are stronger hydrogen bonding and the weaker hydrogen bonding. And then when we tune these bonds to be just the right ratio, then we can have a material that is not only elastic, but also even if you intentionally introduce defect, it can still be stretched over very long, under very large strain without having the crack propagate along the defective sites. So these materials, with these kinds of self-healable material, we started to explore what are the potential places we can start to use these interesting material. So for example, this self-healing material, it can heal even in presence of water, even though it has hydrogen bonding, but the bonding is strong enough so that it can actually heal in water. So this is actually currently how we make these nerve cuffs, so that the nerve cuff contains conductive material and the substrate, then we just wrap around the nerve and the hydrogen bonding will be formed at the interface and allows us to form an intimate contact between the conductive stimulator as well as the nerve. And another thing that these new materials resulted in unexpected potential application is in the area that we term it as morphing. electronics. That is, when we have children, if they have implants, a nerve stimulator, then children will grow over time, and their organ will expand, and their nerve will double in size from a 7 or 8 year old child to adult. But the current nerve cuff is with these kinds of rigid plastic that actually cannot accommodate the growth of the nerve. So with the chemistry that we can develop, then we can essentially, so this is the stress that's applied to these materials, and this is the tensile strength. And then with these materials, we can fine-tune them, both the conductors and the substrate themselves, so that when there's a strain applied very, very slowly over time to mimic the growth of the nerve, then essentially there's no stress being applied to the nerve. And then if you have movement of the person, and in that case, the material can behave more elastic and recover its original shape. So it can accommodate the movement, but while at the same time, with short time scale, it can conform very well with the nerve. So this is a nerve cuff that we put onto the nerve and then wrap around with the self-healing chemistry so that it can intimately wrap around the nerve. And then even after 4 weeks of implant, it still maintains intact without any damage, and we are still able to pick up the electrical signal that we use to stimulate the nerve. So this is an example of basically a material that we try to develop along the line of skin-inspired electronics, and then some kind of side spin-off applications from these materials. So going from insulating material, just now, the material that I mentioned basically is a dielectric material. But going from insulating material to semiconducting material, it's actually more challenging because we have to, again, use these conjugated molecules, which tends to be rigid in order for them to transport charges. And also they form polycrystalline films, which again increase the modulus and make them even more rigid. So learning from the chemistry design that we used earlier, again, we use these hydrogen bonding to incorporate into our semiconductor design. And this results in semiconducting material that has charge carrier mobility that's on par with those of amorphous silicon. But at the same time, now they be able to tolerate strain even as high as 100% without breaking. So this is an array of such stretchable transistor that's made entirely with stretchable materials. And this is another version of such semiconductor. So you can see this is what it looks like, ultra thin, conform to the skin. And this is a new design concept that we found that essentially by induced phase separation, spontaneous phase separation into the semiconductor and the elastomer blend, we can induce nano confinement into the semiconductor. That actually reduces the glass transition temperature or soften these materials significantly. And this allows us to essentially now take any high performance polymer semiconductor and be able to make them highly stretchable and maintain the very high charge carrier mobility. And these kinds of semiconductor can even have a boost in the charge transport if the nanostructure in these materials can be aligned during the coating. So this is actually how we align these semiconductor nano-confined fibers. And through these coating and the coating process, actually align the fibers in the polymer semiconductor. And this gives a boost in the mobility to now to the order of 7 to 8 centimeter per square per volts per second. This is showing, because I mentioned one of the important goal is to have the new added functionalities without compromising electronic property. So this is showing charge carrier mobility of these organic semiconductors developed over years. And then for comparison, of course, amorphous silicon between 0.1 and 1, and then polysilicon above 10. So for organic semiconductor, there are the non-stretchable ones can reach charge carrier mobility above 5 these days. For the stretchable one, the development only started in the around 2014 or 2000, even slightly earlier. But then with the knowledge we learned earlier, then we were able to quickly get to them to similar level now to those of the best polymer semiconductor, but at the same time now adding the stretchability into these materials. So with these kinds of materials development, now we have a collection of materials ranging from conductors to semiconductors, and also some are important substrates. And some of them are stretchable. We also have self-healable version and also biodegradable version. So for every requirements, we have a material that now we can start to play with that gives electronic performance on par with the best other plastic electronic material. So with these, our new form of transistors looks like this. This is a transistor array that we're twisting and stretching, and in the background, the current output you're seeing is from the transistor, and the black curve is the off current. And as we stretch or even poking the transistor, you can see with these new materials, we can maintain the on current essentially unchanged with these transistors. Next, with the transistor, they are only single component. They are the foundation to build electronic circuits. So we spend quite a lot of time to develop the process so that we're able to take these materials, pattern them into the feature size needed, not only just the semiconductor, but also conductor, dielectric, interconnects. And with that fabrication foundation, then we will be able to start to make circuit building blocks, simple circuit building blocks, and also active matrix, for example, for displays, and the sensing mapping for different applications. And the transistors, each batch, we can make hundreds to thousands of transistors. Yield is still in the range of 90%, so still need to be improved. But it's sufficient for us to now start to build some functional elements. So this is a 10 by 10 active matrix small sensing array. At each of the transistor node, we also have a tactile sensor, so that when this ladybug is placed onto the this e-skin surface, so then we can map the location of the ladybug leg. The next one, usually it's a large picture. So this is a small amplifier circuit that we have built. And this amplifier circuit can have a gain ranges from 10 to 25. And if we put two amplifiers together, we can get a gain more than 100. And this amplifier circuit, you can see the gain is independent of the applied strain. So this is through tuning the fabrication so that we can allow the transistor to be to maintain its characteristic and not change at all. And this amplifier circuit is potentially useful for sensing over a very large area when we have sensors distributed over a large area, then the very tiny signal to noise from or very low amplitude of the signal that we collect from the sensor, if they have to travel over a long distance to get to the microprocessor, then we may lose some of the information. So in this case, if the signal is amplified right after the sensing, then this could potentially allow us to map information over a large area. So this is showing the original EMG electrical signal measured from muscle, the moving muscle. And then after amplification, now you can start to see the signal start to appear. So we envision this is going to be used for potentially large area muscle information mapping using this kind of setup. And another approach to try to reduce the variation from potentially from strain, not only from the materials design as well as the fabrication process. The other approach is we're working with our electrical engineering colleague, Boris Merman's group. In that case, through the circuit design, he incorporates units that can allow the cancellation of the impact from the strain so that we can develop functional circuit or functional sensor. In this case, is a temperature sensor made with several transistors. But this temperature sensor is only sensitive to temperature because we see, even though we see a lot of reports on temperature sensor or pressure sensor, but those sensors are sensitive essentially to everything. But in this case here, the temperature sensor is only sensitive to temperature. You see the calibration curve, and then at a different strain, the curve fall on top of each other using the circuit design. So that's another approach we're taking as we go to more complex devices. For displays, so for skin electronics, we also envision having displays on them. Now we have these basic pixels, the RGB that we can build. So combining with the active matrix transistor array, we're hoping that we can realize these kinds of skin display, hopefully in the not too far future. So now I've talked a little bit about the basic concept of skin-inspired materials and their basic functions. And the other area that's really important for the skin electronics is their interface with biological system. So if we have these sensors and ultimately we want the information either to directly input into human or extract the information from human, this bioelectronic interface is essential. There are a number of approaches towards bioelectronic interfaces, mainly developed for neural interface to either transmit electrical signal for electrical stimulation or to collect the information through neural recording. First generation started with these Utah probes. Of course, they are relatively large and also very, very rigid. And then the nanoscale wires can have more bending capability and also the capability to collect information inside the cell. And then the more recent versions are versions that are starting to incorporate flexibility. And also if you make the devices really, really thin and really, really small, and then their bending stiffness is significantly reduced, then they become more compatible with the biological system. In our case, in those cases, they solve some of the problem of the stiffness of these interfaces, but there are additional challenges to address for biointerface. That is the dynamic movement of the organ, as well as the growth or the ever-changing size of these organ. So earlier I showed an example of electronics that can actually grow with the tissue or organ by taking advantage of the new materials we develop. And then this dynamic movement is another area that we see there are a lot of opportunities for these new generation of electronics to address. So for this area, the target for us to develop is a new generation of material that combines the softness of hydrogels that are well known for drug delivery and for tissue engineering. But in that case, they don't have the electrical conductivity. And then combine that with the electrical conductivity that we need, but still maintain the ultra softness of these materials in a new class of material that's called conductive hydrogels. These conductive hydrogels, then the parameters are what we need is high conductivity and high softness. But unfortunately, most of the materials that are known in literature, they are either high conductivity but low softness, or high softness, very low conductivity. So what we want to get is to get the best of both worlds, high conductivity and high softness. So to achieve that, we need to understand how these conducting hydrogels function. So the basic concept here is to allow, so these red units are the conducting polymer pathway or network. So what we need to do is to figure out ways to induce these network to be highly interconnected so that we can get the high conductivity. But at the same time, these conducting pathway are embedded in the hydrogel. And the conventional conducting polymer normally exist as this colloid structure. And there have been studies of tuning the ionic strength to tune the phase behavior of these gels. The trick is to tune the gels so that the conduction pathway can actually be highly connected so that we can maintain the high conductivity as well as the very, very low modulus that's needed in these hydrogels. So this is exactly what we used as the basic concept to tune the material to be in this gel regime by using specific ionic species and then also promote the conduction pathway. So this is one version of such material that we found that using ionic liquid incorporated into the conducting polymer solution, then it can induce these kinds of fiber formation to give us the conducting pathway that's needed to get very, very high conductivity. But at the same time, the material remains highly stretchable, even up to 100% strain, and the conductivity is among the highest known for those of conducting polymer, several thousand Siemens per centimeter. And this is one of the first such conductive polymer that has both high conductivity and also high strain tolerance. But of course, the ionic liquid may be potentially toxic to biological system. So the conducting hydrogel that we finally prepare for interface with biological system Actually, first we form this hydrogel with the ionic liquid, and then we evaporate the water and wash away the ionic liquid. So this will condense into a dry film. And then we can subject this very dense film under conventional photolithography and patterning. So we can pattern this conducting material down to micron feature size. And then we expose this patterned structure with water. And then once it's exposed to water, it will have a expansion. So you see the side view of the expansion. The volume will expand by 6 times. So great expansion of the volume and a lot of uptake of water into this conducting hydrogel. But the conduction network is being maintained so that we have still very, very high conductivity, but then the absorbed water makes these materials have a modulus that's on par with our tissue in the order of kilopascal. So this is the hydrogel that we pattern, and these are patterns that we can produce into these hydrogels with micron resolution. So with these kinds of patterning and a very soft structure, then we can make now probes that are similar to the nanowire probes you've seen earlier that Jacob made before. But these are soft probes. Somehow it doesn't work anymore. Soft probes that you can see can flow around with the liquid and also interface with cells. And they can also be fabricated into the into these large sheets of stretchable sheets that has high resolution of electrodes that can be directly mounted onto the, this is a pig heart, but the resolution can be as high as a single cell, cardimar level. And compared to the previous approach where you have to use some serpentine structure to connect the individual electrode, then the space needed to accommodate these serpentine structure can reduce the density one is able to achieve with these kinds of electrodes. So the high resolution and also high stretchability allows us to put these high density electrode array onto the directly onto the beating heart to map information at very high speed and high density. So this trace shows each square is the information from an individual electrode, and overall from the right to the left side shows the propagation of the electrical signal on the surface of the heart, and from the left to the right is overall 6 milliseconds of data that's collected, and then this very fast propagation of the electrical signal on the heart now can be mapped with this high resolution electrode. And ultimately, one of the things we always have been thinking about while we make electronic skin is ultimately we hope these electronic skin can actually be put onto the wounded arm, and the sensors can directly connect with the nerve system to transmit the sensing information directly through the nerve and then get to our brain. So how do we make that connection between the e-skin and the nerve? Of course, you can use electrodes to make the connection, but in that case, the electrode will have to poke through the nerve or put onto the surface of the nerve. Then you will not be able to specifically excite a particular nerve. And the information we collect from the sensor, there could be the pressure information, temperature information, or shear force information. They have to transmit from through different nerves nerve to get to the right region of the brain. So we have been thinking about how do we get information selectively into the nerve that we want or into the selective neuron that we want. And currently, there's a technology called optogenetics that one of the pioneers is my colleague Karl Desroff. And in that case, they use a virus to infect a certain type of neuron cells so that those neuron cells are coated with a certain opsin that can be stimulated with light so that you can selectively excite certain neurons with light. So the question we have is, can we potentially do something similar as optogenetics, but rather using electrical connection that are genetically targeted to be selective to only certain neuron cells, basically combine the benefit of optogenetics to target certain neuron and also using the natural electrical signal that we can collect from our electronic skin to combine the two together. So our preliminary work together with Karl Desroff group shown that indeed we can potentially use genetic targeting to target certain neuron cells of the type of interest. And then these targeted cell will carry an enzyme that can initiate the polymerization of our conducting polymer. So only the region that's genetically targeted will be coated with the conducting polymer of interest. So on the top, those neuron cells are not covered with this enzyme, but on the lower part, the surface, are covered with the enzyme. And then you see some darker region. These are the conducting polymers that are initiated the growth, and then they grow onto the neuron of interest. And indeed, these are conducting polymer. We can actually measure conductivity. So with that, then now we can target, for example, this is a slice of brain that have a region that's highlighted to be kind of purplish in color. So that's the region that has a genetically targeted growth of our conducting polymer. And depending on the type of nature of the polymer that we select, the conductive or non-conductive polymer, we can now find that they can, in some cases, for the conducting polymer, they may inhibit the neuron firing. But in the less conductive polymer, they actually make neurons fire even more actively. So there's an inhibitory and excitatory behavior that can be controlled depending on the type of polymer that we can actually use to code these neurons. So that could be very interesting as a way to, in the future, for us to, as a possible path towards integration between our electronic skin and our nerve system. So to summarize here, I've shown some design concepts for skin-inspired electronic materials. We now are at a stage there that we have a number of materials at the initial stage that we can start to play with, start to make functional electronic circuits, and start to explore potential applications. And I see there are many possibilities, especially possibility of interfacing such soft electronics with human body. And I know there are a lot of electrical engineers probably sitting in the audience. Whenever I talk about electronics, soft electronics, I always get asked, well, for soft electronics, there's soft electronics, low density, large area, and then we have silicon IC that's so well developed. Then how do these new soft electronics fit in presence of the silicon IC. So what we see is that these soft electronics are not meant to replace silicon IC, but rather to complement or to play in space where silicon IC may not be most advantageous to use entirely silicon IC. So the basic components of any wearable electronics or skin-like electronics will include the sensing module, and then in the middle, data conditioning, basically amplifiers and analog to digital conversion. And then finally, these information will be processed in the microcontroller and our silicon microprocessors, and also wireless communication. So what we see, the area that soft electronics can potentially really play a role is when we have a distributed sensor over large area, and can be distributed sensing, but also high resolution at the same time. But large area is the place where I see the advantage. And then the data conditioning can potentially be made with these soft electronics. That's when we want the data processing, simple data processing to take place right at the sensing front, so that we don't lose the information, and also we can reduce the power consumption for processing a large amount of information. And then finally, the silicon IC will be a small, tiny chip that electrical engineers can now already design, and then these combined together is what we see is the vision for soft electronics and rigid electronics to kind of find the happy place together. And the other vision is we call it body net vision. That is we still need power, we still need sophisticated data processing and transmission functionality, but then we want to take advantage of the soft, stretchy electronics. So then in that case, we separate the sensing onto these stretchable materials and with a simple IC. And then all the rigid components are put into the clothes we wear, potentially the seat we sit on or the bed we sleep on. And sensor you can place on anywhere on your body or even be implanted. Then this way we can truly, is another possibility to truly take advantage of the form factor of the skin-like material. So for example, the outside the body net, and inside body, these are some of the implants we're making where the wireless soft electronics can be embedded just under the skin, and the reader, of course, is outside the body. And then going towards even further future, these are implantable electronics we are very interested in, not only for stimulation and recording of electrical signal, but it's going to be very powerful if we can incorporate measurement also of chemical signal into these soft electronics. So that's another direction that we're moving into. So finally, I'd like to thank my research group, the students and postdocs. They're really the people who did all the hard work and come up with many creative ideas, and also are very courageous to really branch out, to talk to different collaborators and work on different aspects. I didn't switch. And also many collaborators from different parts of Stanford who are working with us to further this field, and of course funding agencies. And again, thanks very much for having me here, and I'll be happy to answer any questions you have. Thank you.
Thanks, Zhenan, for the fascinating talk. So towards the end, you showed your cell-selective polymer coating I think that's a really inspiring idea. So you show that after coating the cells, excitability can change. Did you see any sign of the connectivity between the neurons and the overall activity and functionality of that brain region can be altered as well?
We haven't gotten that far yet. Yeah, it's a project that took many years to get to today's stage. And currently, we incorporated these onto C. elegans, and we were able to see the movement change. But then we haven't yet been able to go into details on the connectivity between neurons. And I suspect, I think we still need to improve on the chemistry to have even better selectivity. Right now, it's basically diffusion controlled and of where gets coded, and also, of course, the competition with the reaction rate. We don't yet have a very good understanding of the entire process of the polymerization yet.
Yeah. Sounds very complicated, but itself can be a therapeutic approach already.
Yeah, potentially.
Without the electron.
Yeah, because you can control excitatory and inhibitory, right, behavior. So then potentially can selectively stimulate certain nerve depending on which kind of polymer is coded, or change the response.
Thank you.
Mm-hmm.
I want to follow up on Chang's question while we look for somebody else. What about the long-term effects? So, as the membrane gets recycled, do you see changes in excitability over time? Do you have to redose with a polymer?
Oh, the over longer term, currently, actually the cells eat the kind of engulf the polymer over longer, more extended period of time. Yeah, so that's another problem we have to figure out how to address.
Thanks.
When you discuss the healing properties of the bioelectronics, that was just in the material themselves. How would you suggest going forwards for developing the bioelectronics so that the circuit designs or the electronics effectively are also healing?
The circuit design, that part we have not thought too much about the circuit healing part. We have been focusing on the materials. That will be a very interesting area, I think, for the circuit designers here. Yeah. There was a question, Dr. Chapman?
Does the contact resistance change with stress?
Yes. Yeah. The question is, does the contact resistance change with strain? Yeah, indeed. For our devices, we did observe there is some change in the contact resistance with strain. So when the channel length is large enough, then this effect is quite small. But when the channel length gets to, in our case, actually below 50 micron, we see more significant contact resistance effect and the dependence on the strain. So one way to get around it is in our fabrication, we can actually put a layer of elastomer as part of the fabrication to control the transistor region to be to experience actually less strain compared to the interconnects. So it's the same density of device we're making, but then the transistor region becomes insensitive to strain. Then in that case, we get very stable electrical behavior.
Result if you start with films that have different width to length ratio, long, one thin, one short.
Right, so the geometry change with strain, exactly. So that's the part. One is we can use circuit design to compensate for that. So if we have for the temperature sensor case, we have a circuit design, so there is another transistor that's not exposed to temperature change. Then we subtract the strain effect in the circuit. And then another case is, again, using the fabrication so that the geometry is actually not changed with the strain.
Yes, I was really fascinated by the PDOT gel that you have, the conductive PDOT gel, and I was just curious, like, does it have any different degradation rates, like the material itself in different biological materials, like neural versus skin tissue? Has you been tested anything like that?
Oh, so for PDOT, normally under biological condition or when it's implanted, it doesn't really degrade over time unless we make them into more like nanofiber structures. Then they may fall apart over time and then get either absorbed by the body or excluded from the body. But the polymer itself does not degrade that easily.
Okay, well, I'm going to fall down the stairs. So we're running close to the end, but I want to remind everyone there's a reception afterward. Jenna's going to stick around if you have questions you want to follow up with. I'm sure she'll be happy to talk to you there. And please join me in thanking her again for the fantastic talk.
Thank you very much.